Hello, welcome everybody, and thanks for being here. My name is Marcos Albe. I am a principal support engineer at Percona. I've been there for almost 12 years. And today I'm gonna share my experience about why MySQL might not be very good for big data, MySQL and other databases. So again, this is a talk about attempts to approach big data analysis using relational databases or document databases. It's my experience, it's my observations through, again, a lot of years working with dozens of customers that have 70, 80 terabytes in a relational database. So, this is a talk not about how to solve it, but what you should expect if you want to do this. This is a talk about setting the right expectations for the database you're using and for the hardware you're using. And it's also an open source tale. I'm not considering proprietary solutions. I'm only talking about open source databases here. What is data? It's a piece of evidence. It's how it says there. It's a fact known for direct observation. It's the price we get for observing things. And it's, for example, the details of a transaction, the information about a person, the population of a country, or the list of students in a class. So all of those are facts. And they are not the same as information, right? Or if we want to go into the details about words. A piece of data on your disk doesn't have too much value or meaning if you cannot later do some analysis on it, right? Like we want to later go and retrieve it. So that is a very important part. And on the other hand, information is that, it's processed data. It's the result of analysis done with the data. For example, we could use the details of the transactions and find that Mondays, students of a certain class and who live in a given city are more likely to buy a certain item. So that's the kind of answers you can get. And you can get incredibly complex answers, but they require you to read the data. So this is how I feel most people when they talk to me about we are doing big data. But jokes aside, let's read a definition from a well-known database vendor. It's Oracle. The marketing says big data is data that contains variety, velocity, and in big volumes. So it's telling us you're going to fill up your disk. And the technical thing is traditional processing software just can't cope with it. It just will not be able to do it. Relational and document databases are designed for efficient transaction processing, adding, updating, searching, and retrieving small amounts of information in a large database. The algorithms were designed for optimal data retrieval performance, not long-term data storage, and thus they are unable to manage big volumes of data. So big data, by definition, is just a large enough amount of data that will give your MySQL a hard time. A somewhat smarter definition is it's a collection of data big enough that allows for meaningful statistical analysis and which normally exceeds modern memory capacity in commodity hardware. And thus, traditional database systems are unfit for doing the analysis we want. So how does it become so big? Well, data becomes big because we acquire it through, again, observations. So imagine a user logging into a retail website. The account data is retrieved, and we record in the log some person logged in at this time from this city. And then searching, this person will start doing searches, and it will, we will store what those searches were, and what day of the week were done, and what time of the day were done. And more session information is acquired as the guy navigates through the site. And finally, he makes a purchase, and we also save the details about the purchase, what items, if he used discount coupons, if he came from a referral website, whatever. So it's acquired through mostly transactional process. But we also have sensors that are automated and are not asking us for anything, or we don't need to interact with them. Or for example, when we swipe the card to open the door in the office, right? Or when you go with your car through a toll booth, and then things are recorded in those events, and data is being stored about those. And finally, of course, Internet of Things. You know, your lamp, your light bulb is sending information about when it was turned on and off. So that could be hundreds of data points, or anything in a smart home is likely collecting data and sending it back to the company. Not great for privacy, but certainly is generating tons of data. And you know, but let's go back to transactional things. So if in a website, if you have enough years of operations and you have enough customers, then you probably already generated a large enough amount of data that it's likely to exceed RAM capacity. And there is an other observation about this. The things that we observe are usually limited. I mean, there's 7 billion humans in the world. That's it. It's like the table is not going to grow more than that. But each of those humans, over time and through different places, they are going to do actions, and those are the actions we record. So big data, or data in general, but when we talk about big data, we consider that it always has a temporal component, right? It has a time component to it. So that is important to keep in mind, because it helps us imagine what we're going to do with the data. Like, you don't say, I'm going to do analysis over a sequence of persons, however you define it. You usually do analysis over a period of time, or a region and time. So that's important. Of course, it becomes big because we keep retaining it. So yeah. And so how much is too much? There is a short answer, and is 4 terabytes in commodity hardware, considering commodity hardware. You know, 4 terabytes is going to be this is about a practical limit. It's not about how much you can store in MySQL. You can store, again, 50 terabytes. You can do, again, I've seen customers with 50 and 70 terabytes in a single instance. But, you know, it's just not practical. It has to be readable, and you have to be able to operate with it. So 4 terabytes is normally what people running a production site will say, okay, if I need to restore the backup, 4 terabytes is a reasonable recovery time objective, right? So that is the thing, is can I comply with my goals when I need to do operations? And can I make it efficient to do the reporting and the analysis? And if you ask guys from, you know, big companies, name it Facebook, Twitter, Pinterest, or whatever, they will tell you they keep their data sets in about that range of size, you know, 4 terabytes. Perhaps there's people, you know, I have customers with 2 terabytes of RAM. Of course, they probably can do 6 terabytes without a sweat, but again, if commodity hardware, let's say 512 gigs of RAM, you know, and a couple of NVMEs, that will be limited to about that nowadays. In the future, it's going to be larger, of course, but I think, and in my experience, people suffers when they have bigger data sets. So the truth is that in transactional databases, it's easier to put the data into the database than later reading it. And that's why people end up with these massive data sets. As the data set required for analysis starts exceeding the RAM, the performance is going to start to degrade, up to the point where response times are no longer acceptable for any business requirements. And it's because, again, transactional software was designed for, well, transactions and not analysis. And it will be very good at that, but they don't want to, it's not meant to scan. It's not meant to do large scans, let's say. And also, the transactional storage is meant to be consistent and durable. And you know, all that also adds overhead. Durability adds overhead, and consistency adds overhead. And that is a key point, right? Because for doing that analysis in a static set where nobody is likely writing in those ranges, you probably don't need that. So what makes it too much? It does not fit in memory, and that's because the data types have overhead. So perhaps I could store, let's say, I don't know, the countries in 1 byte, right? 255 options is more than the number of countries in the United Nations. So 1 byte, I could store all the countries in bitwise format. But then when I do it with, when I actually use the database, the data type, it will be actually 4 bytes more likely, right? Or 2 bytes. So I'm already adding overhead. And not only that, there is a per row overhead. I have it in another slide, sorry. So there's storage algorithms overhead. So the B-tree will have to keep all the pages until you reach to the data. So you have not only to traverse all the B-tree, you have to store it and keep it there and update it. So B-tree, not efficient for that. And LSM, you can which is RocksDB and which is Wired Tiger, you can do incredibly efficient storage. Like, it's very good at compressing, it's very good at intake rate, but it's not gonna be able to deliver on the reads. The reads are amazingly expensive because it has to scan into the past to find when was the last tombstone. And so it says, okay, the data is consistent up to here, so if I found my row up to here, I'm done. So LSM is incredibly expensive for reads, as well as Fractal. Fractal, it's more akin to a B-tree, and it also will have difficulties reading. So LSM, it's okay for point key lookups. You know, if you only do point key lookups, that's fine. Fractal tree might do better with range scans because it can do it on the basement, but it still has to go up the tree to find older versions. So if this is the latest version of the row, so not good. Again, they are designed for OLTP and transactional workloads, and they are very good at this. And then there are random reads. So you can do sequential reads in a B-tree if you are doing a monotonically increasing thing, like time, like IDs, or whatever. Those are monotonically increasing and are easy to scan in a B-tree. But when you do random reads in a B-tree, those are pretty expensive because they have to traverse the tree once and again, and once and again. They have to go down the tree to find that row. So very expensive. You know, then you have, again, ACID overhead. If you want to have transactions, you have to, and you want to have MVCC. So if you want to do, I didn't add it there, but ACID and MVCC, in my mind, they go hand in hand, right? So he can tell you very well. So he's writing a columnar database, and he can tell you very well. So the point is, MVCC and ACID are concepts that go hand in hand very much. And ACID is atomicity, consistency, isolation, and durability. And MVCC is multi-version concurrency control. And it's what guarantees that we can run transactions in parallel, concurrently, without botching each other, right? Like without stepping in each other's toes. And to make sure that when we set commit, and the database told us, yeah, commit is done, things are on disk and are safe and are durable forever. So those are expensive things. And again, you are unlikely needing them for long-term storage and analysis. And then lack of vectorization. This is already going into why you should do something else. In a columnar database, you can use so-called SIMD, S-I-M-D. So single instruction, multiple data. And these are CPU instructions that can be used to take a chunk of rows or a chunk of information and process them in parallel. And it's a way to gain efficiency in reads because you are not dispatching the same function call over and over. You just do one call, and it's a call that is ready to be vectorized by the CPU. The data structures are designed for that, and they use C calls that will hint the compiler that you want to use those instructions, and you will gain massive speed up. This is really important. And as far as I'm aware, no relational database has those. And then this might seem incredible, but random reads from memory are slower than a sequential scan on a good NVMe card. So you can actually try it, and you can use perf to actually track the memory bandwidth and the I/O bandwidth. And they are not too far away. It's perhaps like 5–10%. And it's probably that on a not so good NVMe, memory will still be faster. But the truth is, even if you're in memory, doing millions of random reads, which you might need for analysis, is not going to be efficient. All right, more, what makes it too much? And again, I'm just showing here what it's like typical asymptotic trend for B trees. This is only for B trees. So it literally happens like that as the B tree grows in size, because the pages are of a limited size, and the number of pivots are also limited in a single page in the tree. Then the tree will grow in height and in width, and it's gonna start to degrade performance because you need to go through more pages and then do a longer scan. For LSM and fractal trees, it's worse because they are not fit for reads. They are very good at intake and data compression, but not reads. What else? So, people might tell me, well, what if I only want to keep my data in there, right? Like, okay, I don't want to read it. It's fine. I'm not doing it. I just need to comply with some regulation, and I want to keep 10 years of data. You can, believe me, you can keep it as much as you want, but you are going to be suffering when you have to do operations. Backup is going to take hours, days perhaps. Recovery is also going to be a massive operation, and it's going to be painful. If you ever need to do a consistency check, imagine replication fails on a 70 gigabyte data set. It's like, how do you do a consistency check? Or how do you redeploy the replica? It's just gonna make your life miserable. So consistency checks, DDL deployment. How do you alter a 9 terabytes table, a single table with 7 9 terabytes? How do you do an alter on that, right? It's like, it's not efficient. Can be done, can be done. Is your boss gonna be happy? Unlikely. It's not gonna, things are gonna slow down, disks are gonna fill up, and stuff like that is bound to happen when you have so much data in a transactional database. And then, well, if you ever need to optimize table, you deleted a big chunk of the table. You went ahead and say, okay, my boss gave me the go-ahead and delete the data. Now, to reclaim that space, you need to do optimize. And to avoid all the fragmentation, you need to do optimize. You're done. It's going to take you a day to do optimize. So, and if you have to deploy a dev QA environment with a realistic data set, how do you do that? It's like, again, it's a backup, so painful. And then index cardinality estimates are very likely to be skewed because of fragmentation or whatever. And so you need larger samples. And the larger sample has a larger cost. It's gonna require more reads per index to get proper estimates. Insert latency will grow as the data set grows. Again, we already said the B tree becomes taller and taller and taller. MyRocks has less of a problem with this. Like MyRocks insert rates are pretty stable, like pretty steady. But when it has to do compaction, the compaction can become pretty expensive. So again, in LSM, you just insert. You don't, when you do an update, you don't update this row. You just keep going. And you insert a new row here, and then the guy just, once in a while, it does compaction and it says, okay, these rows are all, like we have a new version here, let's compact everything and put everything in a very orderly file. That process is expensive. And for MySQL, InnoDB, or for Postgres, partitioning can help. So partitioning will make your B tree shorter, but it's gonna limit you on the reads. Again, when you do partitioning, like when you do sharding, what is important is the partitioning key or the sharding key. Like if you split the table by customer and then you want to do a read by cities, you might have to traverse all your shards or your partitions. So that's gonna make it even more costly to read than when you have the huge B tree. So, but we were not talking about reads, so append-only partitioning can help. And most people in this category, you know what they do when they come to Percona support? They tell me, how do I do database recovery? Because they don't have a backup, because it's so unpractical to have a backup with such data set that they just don't have one, and they come with us with data corruption. So what if I want to do OLTP-like queries? Well, yeah, if you're active data set, so you might not want to read your whole data set, and you only read 1 week worth back in time. It's doable, like it's gonna work fairly well. You're still gonna be limited by operations. If your query optimizer ever decides that it needs to do a table scan, it's gonna bring your site down. And it's still limited by memory, as your data set, if it's growing at a rate that it became big data, it's likely at some point not long, like the active data set is unlikely to continue to fit in memory forever. So it might be a reality, and you're gonna have to buy bigger machines in a few years. So it's only good for short ranges on recent data. And I will ask why you're doing this. It's like, why would you keep hundreds of terabytes or whatever you have to only read like, the last week? Rather just, archive the rest, keep what you need, and keep the rest in a steady state in a place you can analyze it. And if the active data set does not fit in memory, then you're gonna suffer buffer pool thrashing and LRU flashing, and the reads and writes caused by the buffer pool management algorithms are literally gonna ruin your performance. So perhaps it's okay if you want to do some reporting during the weekends, and perhaps it's okay if you have covering index, but you can have only so many indexes, because as you add indexes, you're making your data bigger and bigger. So it's not a real solution. You can't cover every query. You can't have covering index for every query. What if I do OLAP queries? Well, again, this has all the penalties we already mentioned, right? It's limited by ACID overhead. The B-tree structure becomes a burden. There is a large per row overhead. You can see there, InnoDB 18 bytes, Postgres is 24, and MongoDB, it's a shame. It's, it keeps, like, if you have 5 fields in your document, and each of the field names is 10 bytes, then you have 50 bytes overhead. So it's quite insane. And that makes it totally impossible to do anything reasonable. Or you trade to very short names, like 2-letter names, which make life miserable for developers. So MVCC, we already mentioning. And LSM, again, we already mentioned it, but these limitations, we're going to see them again, perhaps because they are the crux of relational and traditional databases. This is the problem. And less rows fit in memory, so we read more from disk, because that row overhead in a small table, if you have an OLAP cube, and you have your facts table, and then in a star schema, I forgot the name of the dimensions table. Thank you. And so the dimensions tables are usually small, and they might have 3, 4 integers or 2 integers and some short string. So the 18 bytes overhead might be as big as the row itself. So you're duplicating your data perhaps for many, many tables. So you're going to have to read more from this because things just don't fit in memory. And there's one thing that I haven't mentioned. We read the whole row. So we are reading the whole row when we only perhaps need 2 columns out of the row. So in our facts table, it's going to be a wide table. It's going to be a pretty wide table. But when you do analysis, you don't read all those rows. You read 2 or 3 at a time. All the other ones, you don't need them. Columns. Thank you. So you read only 2 or 3 columns at a time. And the other ones, you don't need them. But still, because you cannot have covering indexes for every query you want to do, you're going to end up reading the whole row. So where you only needed to read perhaps 24 bytes, 40 bytes, you're going to end up reading 300, 400 bytes. And that makes massive, massive, massive difference. It's the reason why columnar databases exist. OK, if you do with MySQL, it has parallel read since 8.0.17, sorry. But it only works on PK or partitions. So it's not like you can solve all the analytics. You can solve some scans, but not do proper analysis and answer interesting questions. Aurora is not open source, and it's incredibly expensive. It has parallel read as well, but again, it's not open source. So I'm just mentioning because people ask me about it. And any of those will have B-tree burden, ACID overhead, per row overhead, and reading the full row. So again, we already went over this. It's just a repeat because it's important to understand this overhead is killing you. It's making your life impossible. What about Postgres? Postgres parallel scan works better. It still has per row overhead, larger than InnoDB even, and still has to fetch the whole row. It's single thread operations like some operations are still going to be single threaded. So you solve the reads, still not the operations, so you're bound by them. And you can do 1 server per query. So for really massive data sets, this will not be a proper solution. And there is a column store in foreign data wrapper in Postgres. It has good compression. I've been reading about it. I don't have personal experience with it. I asked the Postgres guys in Percona to help me with this slide. And it could be a solution for doing analysis, because again, columnar is going to allow you to read only the columns you need. It's going to have better compression because as you put only names in the data set you want to compress, it's going to compress better. If you only use the countries, it's going to compress better. So the data, when compressed by category, by type, by column, it's going to compress better. And then there is a foreign data wrapper for ClickHouse. I, again, haven't used this, but it could be a good choice. But you still have to feed ClickHouse with the data taken from the OLTP database, and then take it back from there to. So I wouldn't be so sure why you want to do this, other than the convenience of not changing your SQL a bit or having a single connection to the database. Again, it exists, it's there. I don't think it's the most practical solution, but it looks like feasible at least. And what if I do OLAP with MongoDB? Well, MongoDB advertises their BI, their business intelligence connector, but that is not open source, so I don't consider it. And here, MongoDB advertised the flexible schema idea for a long time, and I would say it's not a fallacy, but it's a trap at least. Imagine you have a blog site, a website. So you can have, the blog, one blog post could be a single document that will have, the document information and metadata, the author information, and the comments, and it will have the author of the comments as well, right? So if you have that in a single document, when you want to have the answer to who is the people that made the most comments in the whole website, you have to traverse all the documents and find all the comments and then do the count of the authors. And that's pretty inefficient. Like, you cannot answer many questions. The set of questions you can answer somewhat efficiently is limited to the design of the schema. So it's a pretty rigid thing. You have to, in MongoDB, actually, you have to think your schema much more than you will do in relational databases. In relational databases, we normalize the data, and then we can just join, right? So that is the power. Mongo, the lookups are very expensive, and MongoDB will tell you, don't do it. They will tell you, oh, no, just do a single document or do 2 documents and just fetch both. But yeah, it's not very efficient. White Tiger, which is the engine, has an LSM storage engine on disk, but it uses B-trees in memory. So yeah, it's weird. I thought the same. And there is a reconciliation, right? At some point, things have to go from the B-tree to the LSM. That process is expensive and adds latency. And again, because it's LSM, when you want to scan, you pay the LSM cost to do this scan. And it has sharding, yes, but it's limited to 1 sharding key. So if we shard it by city, then when I want to do per customer, when I want to do analysis with the customer as an access, I have to scan all the shards, right? That will be what is called scatter-gather in MongoDB, and it's expensive. And then you are, you might end up with unbalanced shards and hot shards, but that's a tale for another time. The truth is, yeah, sharding can, if you have enough money to put on hardware, sharding could be a solution to do the analysis. You just let it run on 1,000 machines and it works. It's just impractical and expensive. So I don't think this is a very good solution. And it has obscene per row overhead. So you're just wasting money. All of those bytes cost you disk, and they cost you memory, and they have to go through the CPU to be allocated. So all of that is wasting you lots of money. And just in the column names, you have to understand this, the column names are costing you money. So it's very funny. So conclusion so far, you can store as much data as you want, but you cannot really read it efficiently. All these solutions have expensive row overhead. The traditional databases will read the whole rows, and they will pay ACID and MVCC penalties. And compression will not be as good as with alternatives of columnar databases. RocksDB, again, provides a balance between cost of reads and disk footprint. You can dictate when compaction happens and how big the SST files can get. And that could give you either better compression or better reads, but you're never gonna have both. And well, again, operations become a nightmare, and multi-terabyte datasets call for columnar storage. And so let's talk very small bit about columnar storage and why it is the likely right solution for this. Has very low per row overhead. For example, I'm mostly talking about ClickHouse, which is, I believe, best option so far for columnar storage in the open source world. If anybody has other suggestions, I'm glad to hear, because I'm really interested in this, and if someone tells me, oh, I've been trying this, I'm super happy to hear. Has low write amplification. Again, it uses vectorized algorithms, so it enjoys SIMD CPU instructions. There is no ACID overhead. And here is when things get not a bit muddy, but you know, the thing is, in your OLAP, in your OLTP, in your transactional database, you want to have security, you want to have transactions, you want to have consistency. But when you take the data out of there, you no longer require those. So these are not going to be your primary your go-to for recovery. You know, if a disaster happens, you should be able to rebuild this. In other words, if a disaster happens, we expect you to be able to rebuild this. And that's why operations are not such a mess, because we are not taking backups or doing recovery. When we do recovery, yeah, we have to rebuild it, and it's a costly thing, and I don't think there's a way to avoid that. Some costs we're going to have to pay if we want to do big data analytics. And in this case, the cost is building it, and then if something ever goes wrong, rebuilding it. You're going to have to think about how to keep backups of your OLAP, OLTP, your transactions, possibly bin logs, and then do CDC, you know, change data capture out of the bin logs again. You just rerun the process and let it. That can be parallelized, and ClickHouse is designed to store, to do very efficient writes when you send big chunks of writes. Like if you send a write 500,000 rows, super efficient. So that's if you insert one row at a time, very expensive. If you 500,000 at a time, very efficient. So the rebuild is going to take time, but you know, I don't think there's a way to avoid this. But you don't have to do operations. You don't have to do, you don't provision, you know, QA for this. Perhaps you have multiple copies of this, and replicating is, again, it's going to take time. It's like, it's not free. I'm not saying it's the panacea and that it's perfect and free. I'm just saying it's a much better solution. It's still tied to some operations. So, but there is no ACID overhead, and that's important, and there is no MVCC overhead. Has, again, very good compression rates because the columns lend themselves to good compression. It's self-indexed. So here we have covering indexes for any query because the column is the index itself. So one column, it's the index, right? It's like if I want to search by that column, I just go and read that column. So it's self-indexing, and that's what allows ad hoc analytics. It allows us to bring up new questions and be able to run them on the existing data set without doing anything else before. And you read only the data you need. You don't read, like if I want to read the names on a row-oriented database, I have to read, if the name is not indexed, I will have to read the whole row just to bring this one column. On the column-oriented database, if it was thrown here, I will have the names in a single segment that I will read sequentially, and that will be sequential reads. And again, that's a whole difference, you know. It has specialized aggregation data structures. So ClickHouse is very low-level optimized. It has a ton of low-level optimizations, and it has, I guess it's like 32 aggregation algorithms. So depending on what type of aggregation, what type of data you're aggregating, and a bunch of other conditions, it's going to choose one algorithm over the other just for efficiency. So it's really adding efficiency at the low level. And again, this is all about the nitty details, right? It's like the row overhead, what algorithm you use, and all those, they start counting when you have billions to do. And then it can be massively parallel and distributed. You can run a query with all the CPUs of one server or 5 servers. So you can really scan large amounts of data with this. Again, I have a longer presentation about columnar databases. If anybody is interested, I can show you that later. So retention and archiving. These guys here were telling me his boss doesn't want to delete data. And you know, it's kind of, okay, you don't want to delete it, perhaps we can do other stuff. Like you could, first of all, there's usually little sense in eternal retention. Like, why do you do it? It's like, if you want to do analysis from data this back from 2005, consumer habits changed in the last 17 years. So I don't think the data is going to be valuable for the business, right? And data has to be valuable for the business. Otherwise, it's money wasted. If it's required by compliance, then there is a retention limit. And what you can do is, if you're not reading the data and you're keeping it for compliance, you can compress, and you can use the archive engine or MyISAM with MyISAM pack. They will deliver very high compression. They're going to shrink your table perhaps 40, 60%. MyISAM is not evil or you know, it's not going to make you sick. It's just not good for concurrent writes. But reads, I don't think it has any big problem. Yeah, well, check something. Yeah, well, and that, and yeah, if you know, if the database crashes, the table might come out corrupt, but it's unlikely if you're not doing writes. And again, it can be good for reading. It does. Again, the archive engine, I will never write within it like with it. I will never use it for. You can actually do updates and deletes in there. It's not like it's archived and freezed. It's like it's usable, but I will never do it. I will just use it, you know, as a secondary storage for long-term retention. That can still be queried, right? And it can be queried fairly efficient. And then you should archive or purge stuff, right? Just delete all data that is no longer considered relevant. And if required by your boss, show them scalability costs. You know, show them how much they are spending on drives because they are having 18 bytes per row overhead. And you know, like if you do your math and using information schema, you can query your tables size, right? Like you can do the math of how big is this row, how much is the overhead I'm paying for each of these rows, and as a percent, right? And so that will give you material to tell your boss, hey, this is costing us 40% more than is necessary. And then if he's doing reports, you might be able to get away with using pre-aggregated tables. That requires code changes or periodic refresh of the pre-aggregations. But it is an efficient way to answer many, many questions pretty quickly and without doing too much magic or switching databases. So disk and memory are equally affected by data footprint. You should drop unused indexes, drop unused columns, reduce data types to optimal ones. Like I see people using big int in their customers table, like for the ID of their customer table. And I remember Yves Trudeau telling me, big int is enough to count the ants on Earth. So unless you have ants as customers, it's unlikely you need it. So switching to proper data types that are fit and that have the less waste per datum is the best. The primary key is especially important in transactional databases because it's stored also in the secondary keys. So each secondary key has a copy of the primary key. So if your primary key is double the size it needs to be, it's adding double the size to also the secondary keys. Again, purge all data, archive all data. You can also do binning and histograms to solve other type of analytics. And okay, for some cases, you know, you can, sometimes you don't need to read the whole row. and you know that very well, and you know that's not going to change. And I would say split the row in 2 tables and have one table with the part of the row you truly read every time, and the other part with the things you store there just for once in a while. That might be an efficient solution.
It's a common data warehouse solution.
Huh?
It's a common data warehouse.
Yeah. It's not uncommon. It's just people don't do it very often. And that's it. We still have 5 minutes for questions. That was good timing, man. No questions? Then we call it a wrap. Or you can reach me on the alley, on the hallways after my next talk, which I have to run to in a few minutes. But after my next talk, which is God knows where, I need to find out the room. But I'm going to be doing a PMM presentation. If you are wondering how we monitor databases, you will enjoy that one. Folks, thanks for attending, and let us, again,